For the next 6 lectures, it's my great pleasure to introduce you to the earth sciences, which is my own first and favorite scientific discipline. We're going to learn about the materials that make up the earth, the solid and the liquid and the gaseous parts of the earth, and we're going to look at some of the phenomena that occur both on the surface of the earth and deep inside. But most of all, we're going to explore the great principle that the earth shows billions of years of gradual change. In Lecture 37, I'm going to examine the nature of the change that occurs on our dynamic planet. And I'm going to divide the lecture into 2 parts. First of all, I'm going to begin by telling you about 2 of the most violent and destructive events that can occur on Earth's surface, that is, earthquakes and volcanoes. But geological change isn't always violent. It can also occur through gradual change, through processes like erosion and sedimentation and uplift. And we'll look to see how those processes can lead to dramatic change as well. So let's begin this lecture on geological change. Now, in the last lecture, we saw that Earth is in many respects just an ordinary terrestrial planet. That is, it's similar in size to Mercury, Venus, and Mars, only slightly larger than Venus, maybe twice the size of Mars, but very typical in terms of the size. It's also typical in composition to the various terrestrial planets. Recall that the main element in these planets is oxygen with magnesium, silicon, and iron. And all 4 terrestrial planets share that characteristic. All the terrestrial planets are very similar in terms of their orbits. If you look down on the north pole of the Earth, its orbit is basically counterclockwise, and that's true for all of the planets. And indeed, it's true for the rotation about Earth's axis as well. You orbit counterclockwise, you rotate counterclockwise, and except for that unusual case of Venus, which has a very slight rotation the other way, all the planets, especially the terrestrial planets, have that counterclockwise sense. And finally, remember the Earth is a layered planet. All the terrestrial planets formed during the Great Bombardment at the very late stages when the protoplanets were being bombarded constantly by asteroids and comets. Huge amounts of gravitational energy were being brought in. The planets were essentially molten, or at least largely molten balls. And when that occurred, you had the process of differentiation, where the most dense materials, the iron metal, the nickel metal, sunk to the very core of that protoplanet. And then you had a large mantle formed of dense minerals of oxygen, iron, magnesium, and silicon. And only the very lightest materials went to the outside, to the crust. And so the Earth, like the other terrestrial planets, is layered. One big difference, though, is our Earth is one of the most dynamic bodies in the solar system, much more dynamic than the other terrestrial planets right now. And we'll see why that is, the result of dynamic movements deep within the Earth. Now, on the scale of a human lifetime, the Earth's features, the major features such as the continents, the oceans, mountains, valleys, they seem unchangeable. Indeed, over dozens of human lifetimes, those features would seem absolutely fixed and permanent. But a closer look will convince you, I think, that the Earth is a planet characterized by constant global scale change. If you look at the Earth's surface, there are many, many signs of change. And some of those agents of change are quite violent and sudden. Earthquakes, a sudden shaking of the ground. Of course, volcanoes, where new rock pours out in a molten state onto the ground. But there are other natural processes that achieve change rather slowly. We have erosion, we have weathering. Rivers and streams can carve valleys over very long periods of time. So these are gradual processes. I want to first look at 2 of these violent processes, the earthquakes and the volcanoes. Earthquakes. They're a sudden shaking of the ground, a vibration of the ground, and it's caused by a sudden crack or break in rocks that then slide past each other. And when this rock suddenly shears or breaks, then you have a violent motion of the ground. It sends basically a sound wave, a shock wave through the ground. When this occurs, the ground can actually move up and down like a wave if it's a particularly violent earthquake. People who have been in earthquakes describe this feeling of being on a ship at sea. Suddenly the ground is no longer solid. It actually is moving in this very strange wave-like fashion. Of course, most earthquakes are undetectable. But the most severe earthquakes can be absolutely devastating. There was an earthquake in 1976 in Tangshan, China. It killed 250,000 people. So earthquakes are poised in many places around the world to cause great damage. Now, an earthquake results from gradual buildup of stress in two blocks of rock that are in contact with each other. Stress builds up because rock surfaces are irregular. They don't just smoothly slip by each other, but they're locked into place. And as the stress builds up and builds up and builds up some more, suddenly you have a release of energy as the two rocks slip by each other. When they slide by each other, sometimes by as much as several meters, you can have a slip that's, say, 10 feet or more in some extreme cases. It releases huge amounts of energy. Now, the energy that's released during an earthquake is quite analogous to what happens in many everyday situations. For example, when you tightly stretch a rubber band and then it snaps, or you blow up a balloon and it bursts. And let me show you an example. If you take a pencil and put it between your fingers, you can apply a stress to it. Now, you know at some point it's going to break. The question is, when? It bends farther, you hear little pops, but not quite. And then suddenly, when you get stretched to the point, bending more, and then suddenly it breaks. Now, one of the problems with earthquakes is, how do you predict when it's going to happen? That sudden release of energy, it causes the ground to oscillate, it causes things to shake, it causes tremendous stresses on buildings. And yet, we don't know when exactly it's going to happen. We know the stress is building up. It's very difficult to predict. Now, you sometimes, as in the case of the pencil, might hear little premonitory cracking, little tremors that occur before the earthquake. And that's one way of perhaps leading up to saying, well, sometime in the next week or month or year, you might have a big earthquake. But to say the exact day or the hour is almost impossible. In characterizing earthquakes, one of the important things is to know the severity of the earthquake. And there are a couple of different scales that are used to describe how severe an earthquake has been. One of these is the Richter scale. This was devised by the California seismologist Charles Richter in 1935. Richter's scale records the amount of ground movement, and it does this in factors of 10. So a magnitude 2 earthquake causes 10 times more ground movement than a magnitude 1. If you have a magnitude 5 earthquake, it's 100 times more ground movement than a magnitude 3. What's really scary about this scale is that the amount of ground movement in factors of 10 corresponds to energy changes in factors of about 33. So each increase of 1 in the Richter scale is an increase in 33 times the amount of energy. So we have a very large scale, and the most intense and destructive earthquakes have very, very large energy contents indeed. Now, as you might expect, the small earthquakes are much more common. Every year, there are hundreds of thousands of quakes recorded around the world in the 2 to 3 Richter scale range. But the largest possible quakes, which are somewhat larger than 8, occur only about once every decade. To give you a sense, the 1906 San Francisco earthquake, which destroyed that city, is estimated to have been a magnitude 8.3 earthquake. There's a second scale that's used, that's called the Mercalli intensity scale, and that records the destructiveness of an earthquake. So you measure an earthquake not by how much the ground moves, but just by how many buildings fall down, in effect. It's a scale from a Roman numeral 1 to Roman numeral 12. A level 1 Mercalli earthquake is not felt by people at all. You need a very sensitive seismometer to detect it. A level 12, on the other hand, completely destroys every human structure in the area. And once again, to give you a sense, that San Francisco earthquake in 1906 is estimated to have been a Mercalli 11 earthquake. Both Los Angeles and San Francisco in the United States are near major fault zones, very much capable of magnitude 8 earthquakes again. And indeed, the big concern in this region is not if such an earthquake is going to occur, but when the next one is going to occur. Because big earthquakes are just a matter of life. It occurs over and over and over again over the centuries. Now think about how earthquakes can cause large-scale changes over time. Each time an earthquake occurs, 2 blocks of rock move with respect to each other. One block may move slightly to the north, one block slightly to the south with respect to each other. Now, each earthquake causes only a few feet movement maximum, but if you continue this process year after year after year, decade after decade, integrated over thousands and then millions of years, it can cause very large changes. The San Andreas Fault, for example, in California, it ruptured during the Great San Francisco earthquake. That was the main fault system involved there. It extends more than 1,000 kilometers, and over the last few million years, it's moved literally hundreds of kilometers. And so small changes integrated over long periods of time end up causing large changes on the surface of the Earth. I think this behavior underscores the recurrent theme of this lecture, that all kinds of small incremental changes in geology integrated over long periods of time lead to big changes. Same thing's true for the other dramatic and violent event on the Earth's surface. That's volcanoes. And volcanoes are a great example of how small incremental changes can lead to big changes over long periods of time. A volcano is a mountain or some other feature that spews out molten rock and therefore causes new material at the surface of the Earth. It can be either on the land surface or at the bottom of the ocean, on the ocean floor. All volcanoes require a plumbing system. You have to somehow bring molten rock from the interior up to the surface. And so if you can imagine beneath a volcano, you have pipes and conduits through the rock. You may have a magma chamber, or you may have a system of cracks and fissures where that molten rock accumulates. And then gradually the pressure inside the Earth is large enough that it forces that molten rock up and out onto the surface. That process may be facilitated by the fact that magmas generally dissolve and incorporate water, H2O, and CO2, which are volatiles and gases, and these help make the melt more fluid. Also, as the material comes near the surface, it causes more of a violent eruption, more of an explosive kind of behavior as those gas bubbles burst and explode, much like a Coke bottle. If you shake it up and open it up, it'll foam all over the place. Volcanoes can do the same sort of thing. Now, many magmas, like the black basalts that flow down the sides of Hawaii's volcano, those are often quite fluid. They can often flow down the sides and the flanks of the mountain for miles, and they cause damage, but they very rarely cause death because they flow in a stately, slow kind of fashion. Photographers can move right up to them and take a picture and walk away safely. So even though those are dramatic volcanoes, they're not particularly dangerous. But there are other magmas, those especially rich in silicon and oxygen. And remember, silicon and oxygen bonds are very strong, and they form stiff arrangements like glass-like materials. They are such stiff and hard magmas that even though they're in a molten state, they sort of come welling up in a very viscous, very rigid sort of mass, and they can plug the top of the volcano, and then pressure builds up, and it builds up, and it builds up some more, and the volcanic eruption is not a smooth lava flow, but rather an epic explosion that spews out hot gases and incandescent debris that can flow down the mountain at almost supersonic speeds and killing everything in its path. Much, much more dangerous. That was very much like the epic explosion that blew off the top of Mount St. Helens in Washington State in 1980. Expanding gases play a very important role in both these kinds of eruptions. They can create spectacular lava fountains and basalt like you see in Hawaii or in Iceland, and also they can cause that explosion as the pressure cooker effect takes place in more viscous magmas. It's a sobering fact that even in North America, there are hundreds of thousands of people who live near and around the shadows of volcanoes. The most dramatic of these volcanic activities occurs, of course, in Hawaii, where the very slow flow of lava destroys many homes on an annual basis, but nevertheless does not take a lot of lives. But much more dangerous are the kinds of volcanoes that occur near Washington State and Oregon State, the type of volcano near Mount St. Helens, where mountains like Mount Rainier could in fact erupt in a very violent, very sudden event and cause a much larger loss of life and property. When Mount Pelee erupted in the Caribbean island of Martinique in 1902, this is an example of this kind of volcano, 29,000 people were killed instantly. And so, of course, similar fates could befall the residents of Seattle, Tacoma, for example, and other areas of the United States near those big volcanoes. As dangerous as volcanoes are, it is possible to make some predictions about when they might erupt. And much effort is going into volcano monitoring of this type of volcano. Around Mount St. Helens, for example, before its big eruption, most geologists knew that there was going to be an eruption sometime soon. And they knew this for several reasons. For example, they could see a gradual swelling of the top of the mountain. You measure the altitude or just the shape of the top of the mountain, you can see it bulging out. You can do infrared measurements. You can measure the heat flow coming out of the top of the mountain. And as magma comes closer to the surface, the top of the mountain actually begins to get hotter. You can also make seismic measurements because as the magma is flowing towards the surface, you have small earthquakes, small shaking of the ground, which causes the whole mountain to jiggle as the magma is working its way up. So people knew that Mount St. Helens was going to erupt. And even so, 57 people died in that eruption, including several volcanologists who were studying the volcano. I know that volcanoes seem like remote phenomena. They seem like they're not very common in our everyday life. But it might surprise you to know that they have really played a major role in shaping the planet. In fact, 80% of the Earth's crust includes volcanic rock as part of the surface. 80% of the Earth's crust, even though volcanoes seem very remote. It's because volcanoes, even though they erupt only occasionally and only in a few places, over geological time, as you add up this material over millions of years, you start creating a layer, a mantle over the entire surface of the Earth of volcanic rocks. The doctrine that great geological change can take place through countless decades of gradual increments is called uniformitarianism. This idea is in sharp contrast to catastrophism, a competing doctrine which argued that most of the Earth's features arose through violent events, particularly one dramatic flood. This debate raged 200 years ago, and the founder and the great champion of uniformitarianism was James Hutton, a Scottish geologist who lived from 1726 to 1797. Now, it took Hutton some time to find his true calling. He was first unsuccessfully apprenticed to a lawyer. He then earned a medical degree, but he never practiced medicine. He did, however, achieve great success as a farmer because he used new experimental methods and he actually designed new methods for agriculture, which made him a wealthy man at a fairly reasonable age. So by his early 40s, he was able to retire to study geology, particularly in the area around Edinburgh. He particularly enjoyed the rich intellectual life around that city in the 1780s and 1790s. Edinburgh was an amazing place in the late 18th century. At this time, the prevailing wisdom was that the Earth was about 6,000 years old. That's all. And this is in accordance with the literal interpretation of the biblical chronology, particularly the chronology proposed by Bishop James Ussher, who lived from 1581 to 1656. Under such a climate of religious thought, very few people thought about the implications of millions or hundreds of millions or even billions of years of change. But Hutton was different. Now, at the time, most geological features were interpreted as the result of the one great catastrophic flood. That was the Noachian deluge. And this belief supported two prevailing geological doctrines of the 18th century. The first, as I mentioned, was catastrophism, that geological change occurs through catastrophes. The second was called Neptunism, and that's the idea that rocks are formed primarily through the action of water, either as sedimentary layers of particles deposited one on top of each other, or often through chemical precipitation. And many people thought that basalts and limestones were just chemical deposits precipitating out of water. Well, Hutton differed. He realized that the most dramatic changes in the Earth's surface are told by the testimony of the rocks, in outcroppings, in cliffs. And he traveled from outcrop to outcrop around his native Scotland, and he learned the dramatic story that the rocks had to tell. One of the greatest discoveries was Hutton's interpretation of a remarkable cliff near the town of Jedburgh in Scotland. That's about 35 miles east of Edinburgh. And this epitomizes the way he thought about rocks. At this rock outcropping, there are intensely folded layers of rock at the bottom of the hill, very, very intensely folded, but they're cut off. And on top of those rocks then are layered flat-lying sediments in layer after layer, also containing evidence of sedimentation, also containing fossils, by the way. So in these rocks, what Hutton saw was a succession of periods of sedimentation, of burial, of compression and folding, and then uplift and erosion a whole sequence of events, each one of which had to take millions of years. So imagine this. First, he said there must have been some shallow ocean or sea, and sediments were deposited layer by layer in a flat-lying way. Then those layers had to be buried. They had to be heated. They had to be compressed and turned into rock layers. Then some great forces, tectonic forces, came along and squeezed them so that those flat layers became intensely folded. And that had to have occurred deep underground. Following that, there had to be a period when all those rocks were uplifted to above sea level, because you saw that erosional feature. You saw that they had been truncated and cut off. And that's an erosional feature. Then they had to be buried again under another sea or ocean. Then there had to be more layers of sediments deposited. They had to be buried deep enough so that those layers were turned into rock. And finally, the whole thing had to be uplifted once again, cut by some river or stream so that you saw the cliff face, so that James Hutton could look at these deposits and figure out what they were. What an epic story in one outcrop, a story that clearly took vast amounts of time. In all these processes, Hutton also saw the Earth's inner heat as an essential agent of change. And this point of view is called volcanism, in sharp contrast to Neptunism. So here's Hutton saying, rather than catastrophic events and water being the principal agent of change, you also have to look for immense periods of time and heat being an agent of change. Well, over and over and over again, he said, these processes have occurred. And the cycles take tens or hundreds of millions of years, maybe even longer. He just didn't know. He saw no way of telling how long the vast spans of geological time were, but certainly to be limited to 6,000 years was an absurdity in his view. Hutton's ideas were published in a revolutionary but largely unreadable text called The Theory of the Earth from 1795. In Hutton's own words, he said, "The result, therefore, of our present inquiry is that we find no vestige of a beginning, no prospect of an end." Unfortunately, the way Hutton wrote was so indecipherable in the text of his work that most people just ignored it. But Hutton's great friend, John Playfair, also a resident of Edinburgh, aided the acceptance of uniformitarianism by his very persuasive popular account, Illustrations of the Huttonian Theory of the Earth, which was published in 1802. It's so often true in the history of science that a great idea will be ignored until some champion comes along who can articulate it, put it in everyday language that people can understand, like a persuasive legal brief. So truth isn't always enough. Sometimes you need to have the persuasive argument to make people see and realize and accept that truth. Well, there are many, many other examples of the dramatic consequences of slow, cumulative change, and you can see them all over the world. Anywhere you drive your car, any of the national parks where there are geological formations, you can see evidence for these great changes. The Grand Canyon, Yellowstone Park, any of the national parks. It's wonderful to think about geology in the context of the great natural wonders we have in North America. In many places in the world, including the absolute highest mountains in the Rockies, the Alps, in the Himalayas, you find fossils of sea creatures at the highest point. At the very top, the highest-most rocks of Mount Everest are limestones that were deposited once in an ocean and have somehow, over geological time, been uplifted to the highest land point on Earth. I've had the opportunity to study some of these rocks in the Canadian Rockies at very high altitudes, at 10,000 feet. You climb up and you climb up and you climb up through the forest line, up above the forest line, into the area where trees can't even live. And there the rocks are beautifully exposed. And at the highest points of many of these mountains, you also find clear evidence that sea creatures once lived. These animals that you find fossilized in limestone at the highest points of the Canadian Rockies once lived in oceans. And somehow those rocks have been buried, they've been hardened, and then uplifted again to the point that they're 10,000 feet above sea level. You see that all over the world. There are many other examples. All across northern United States and in Canada, you find scrape marks, you find piles of loose boulders that indicate that North America was covered by glaciers. Sheets of ice They must have accumulated over thousands of years, gradually advancing down over Canada, covering almost all of Canada, covering the northern states of the United States, pulling boulders, scraping rocks as they went. And then as the glaciers retreated, they left behind these huge piles of glacial boulders and other sediments, indicating epic periods of time. And all that glaciation just occurred within the last few tens of thousands or hundreds of thousands of years, just a geological blink. And yet, it's hard to imagine how glaciers could advance that far and cause that much change. We see huge deserts, and the deserts are composed of countless tiny grains of sand. All those sand grains were once part of rocks, and wind and weather and erosion had to erode those sand grains, and then wind had to blow them into an area. And you stand in the middle of a desert and you look around you and imagine all of those sand grains once being part of solid rock. And much of that rock used to be underwater. For example, sandstones that were formed near beach-type environments, buried, compressed, heated, becoming solid rock, then being lifted up and eroded to form the modern-day deserts that we see. Once again, epic cycles of change. I realized even with the occasional earthquake or volcano, it's difficult to see any dramatic change on the Earth on the scale of a human lifetime. So, is it possible that these kinds of dramatic changes I'm telling you about occurred once in the Earth's past but are not occurring now? I'd like you to think about this in terms of just a common experience. If you've ever hiked in the mountains or on the hills, you've seen streams running down the sides of these mountains. I want you to think about the erosion process and what must happen. We're going to do what's called a back-of-the-envelope calculation, a very simple calculation to show that indeed these processes are going on today, and that even the tallest mountain in North America can't last very long in the context of geological times. Now think about the erosion of a mountain. A typical mountain in the Rockies, for example, can be thought of a mass. Imagine it about 2 kilometers high, with a base that's roughly 4 kilometers by 4 kilometers. Now, every mountain is different, but just think of this as a typical mountain, 4 kilometers by 4 kilometers by 2 kilometers high. And so you can think of that as a volume that's just roughly, as again, a back-of-the-envelope calculation of 2,000 times 4,000 times 4,000 meters. That's roughly 32 billion cubic meters of material. Cubic meter is about a little more than 3 feet on a side, so you can visualize a cubic meter, but 32 billion is a lot of cubic meters. Now, mountains typically have half a dozen or so streams that flow down their flanks, and these streams carry small amounts of sediment. That flow rate is usually greatest during the spring thaw, but you can imagine that each stream averages perhaps a shovel full of dirt and sand carried down the mountain each day. So a shovelful isn't very much, just a pile that would fit underneath a small chair. And from each of these 6 streams, then, you have a shovelful or so. That's maybe a 20th of a cubic meter. So you can multiply this out, and you can say in a year how much sediment comes off a mountain in a just very simple, once again, a back-of-the-envelope calculation. So you have 365 days in a year times a 20th of a cubic meter a day times 6 streams, and that comes out to roughly 110 cubic meters of sediment coming off a mountain each year. Now, that's not very much. That's just a couple of dump trucks full, really. So how long would it take to wear down a mountain at that very leisurely rate of 110 cubic meters a year? Well, you divide 3.2 billion by 110, and the result is 290 million years. 290 million. That's a blink of an eye compared to the 4.6 billion year age of the Earth. In other words, if the Earth's been here for 4.5 billion years, and a tall mountain in the Rocky Mountains, even with the leisurely erosion rate, is going to disappear in roughly 300 million years, there have to be processes going on right now that are building mountains. The dynamic processes of the Earth must be going on even as we speak. So we're going to have to think a lot more about how these geological changes take place, and we're going to have to look beyond the crust of the Earth to what's going on in the deep interior. Well, in summary of this lecture, we've seen that the Earth is a dynamic planet. It's constantly undergoing change. Some of these changes, like earthquakes and volcanoes, are sudden and they're violent. Others, like erosion and uplift and sedimentation, are much more gradual. But all of these geological processes, acting over millions of years, lead to dramatic change and alteration of the Earth's surfaces. Our studies of the rock prove beyond any doubt that mountains are still being formed on the Earth. And the processes by which mountains are formed, the processes of tectonics, are the subject of the next lecture.